All right, so we are looking at section 3.2, logarithmic functions and their graphs, and I am live with block 2. Block 2, you want to give a shout out to everybody watching? Okay, so in section 3.2, we get to learn about logarithms. Remember that exponential functions pass the horizontal line test. You know that the exponential function might look something like this, and it passes a horizontal line test, which means that exponential functions will have an inverse. And the inverse of an exponential function is a logarithmic function with whatever the base is. All right? And up again. Okay, so our definition of logarithmic function of base A. For x greater than 0, a greater than 0, and a not equal to 1, y equals log to the base a of x. That's how we read this. Can you all read this with me? Log to the base a of x. Log to the base a of x. Log to the base a of x. If and only if x equals a raised to the y. All right? So this is written in exponential form. This is written in log form. All right? The function given by f of x equaling log to the base a of x, and I'm even saying read it log to the base a of x, I'm telling you how to read it, is called the logarithmic function with base a. You don't have to write all this down, but just so you get the idea that these are identical. All right, so let's see if we get some more clarity here. So the equations y equals log to the base a of x and x equals a to the y are equivalent equations. One's just written in exponential form, and the other is written in logarithmic form. So let's practice doing this. Because the vital thing in this section is being able to go from exponential form to logarithmic form or vice versa. So let's start with this first equation. It is 3 to the 4th equals 81. Is this on your gift? It is? Okay, so we're going to write 3 to the 4th equals 81. So in log form, that's going to be log to the base what of what equals what?
Log to the base of 4.
Base of 3.
So look, what do you see here? We see our base is a here, right? And so our base goes here, right? So what's our base here? 3. So the 3 has to go here. Everybody agree? And then the power, the y is our power here, right? That's our exponent. And that is the logarithm. So that has to go by itself, right? So what am I going to put over here?
4.
4. That's our power. Everybody agree?
Yeah.
And then the what we get when we take a to the y, whatever that is, that's x, that goes right here. So really, what am I going to put right here? 81. So how I want you to read these and think about these, log to the base 3 of 81 is equal to 4. The way I want you to think of this is 3 raised to what power gets me to 81. That's what we mean by logarithms. 3 raised to what power will get me to 81. All right, and the answer is 4, because 3 to the 4th gives me 81. Okay? All right, so let's try this one. We're writing log to the base 2 of 32 equals 5 in exponential form. So we're going the other direction now. We're going from log form to exponential form. So if we try that, I want you to fill in these boxes. Something raised to the something equals something. This would be exponential form. Can you help me out with that, Dylan?
2, and then the box above it will be 5 equals 81.
So 2 raised to the 5 is equal to 32. Do people agree with this? All right, so that's how you go from exponential form to log form or log form to exponential form. All right. Very important to point out that logarithms are exponents. So in this case, the log is 5, right? The log to the base 2 of 32 is 5. So 5 is the logarithm, and that means that 5 is our exponent, right? All right. So that means log to the base a of x is the exponent to which a must be raised to obtain x. You don't have to write that down, just so you are understanding what we're doing. And a little practice with just some symbols. If I got log to the base star of heart equals hexagon, can you arrange these somehow so that I get this in exponential form? So what raised to the what equals what here? Grace J.
Hexagon to the star equals heart.
Hexagon raised to the star equals heart. Do people agree with that?
Oh, wait, no.
Dane?
The star and the hexagon need to switch places. So the star's the base.
Like this?
Yeah.
Yeah.
So this is log to the base star, so star's got to be my base over here, of heart equals hexagon. The hexagon is the log. That means the hexagon has to be my exponent. Does that make sense? So we would write that way. Okay? All right, what about this one? Rewrite in logarithmic form. P raised to the g equals s. How are you going to rewrite that, Hannah? You're going to fill in log to the base what of what equals what?
Log to the base p of g. No, log to the base p of s equals g.
Log to the base p of s equals g. Do people agree with that
Yes.
arrangement? Because our base here is p, so that's what we put here. Log to the base p of s equals g. Our exponent is the log, so that's got to go by itself. All right? Okay. So what is the log to the base 4 of 16? Well, this is really saying 4 raised to what power gives me 16? So that would be equal to 2. So log to the base 4 of 16 is equal to 2. I'm sure to give you some kind of a non-calculator quiz where you're going to show me that you understand how to evaluate logarithms, what they mean, and what they're going to equal. All right? Okay, so let's practice some of these. If I have, is this on your gift?
Some of them, yeah.
Some of them? All right, so this is saying if f of x equals log to the base 3 of x and x is equal to 9, that means I can think of this as log to the base 3 of 9. And what's that going to equal, Nick? Why?
There's 3 squared.
All right, log to the base 3 of 9 is equal to 2 because 3 squared gives me 9. 3 raised to what power gives me 9? How about this next one? This is log to the base 2, and I'm plugging in 8 for x. So that's going to equal what, Avery? How do you know? Because and this is correct, it's because 2 raised to the third power is equal to 8. Yeah, 2 times 2 times 2 gives us 8. Are we okay with this? All right, what about this one? This is log to the base 5 of 1. Log to the base 5 of 1. What's that going to equal, Justin?
0.
How do you know?
5 to the 0 with the power is 1.
All right, that's because 5 raised to the 0 is going to equal 1. All right, how about this one? Log to the base 3. Log to the base 3 of 1 over 81. Dane?
What would be negative 4?
Why negative 4?
Because if you have a negative exponent, doesn't it put it into a fraction? And then 3 to the 4th would be 81.
So you're saying it's going to be negative 4 because 3 to the negative 4 is equal to 1 over 81?
Yeah.
Do people agree with that? Because 3 to the negative 4 is the same as 1 over 3 to the positive 4, and 3 to the 4th is 81. So I agree with Dane on that. Are we okay with this? Okay. The logarithmic function with base 10, because here's base 3, we have base 3, we have base 5, and so on. But if we have base 10, that is called the common log. All right? And it is denoted log to the base 10, like the little 10 is the base, or simply log. So if you don't see a base, it's understood to be common log, base 10. All right. So let's try evaluating some common log functions. So if I've got f of x equaling log of x, notice no base written in, so it's understood to be what base? 10. And if I want the log of 100, what's log 100 equal to? Let's see. Log 100, Grace K. Remember, this is really base 10. You want to write it in, you can. You don't have to.
Okay, so 1, no. It would equal 2,
Why?
because 10 squared equals
Because 10 squared gives us 100. Everybody okay with that? All right. Okay, so we did that one by hand. I don't think we can do the rest of these by hand. So grab your calculator, and on your calculator, we're going to try log 1/5. So on our on our calculator, hello, I'm just going to a calculator page, and I got to clear that ink off. So in this case, to find log, do you see how it's like right here at the 10 to the x? So I can just do log, and it's letting me choose whatever base I want. Now you're very fortunate to have the TI Inspires, because if you had a TI 83 or an 84, it only let you do base 10, or we're also going to learn about base E, right, for logarithms. But you can choose whatever base you want. But in this case, we do want base 10, and what was it supposed to be? 1/5? 1/5. And I wanted this as a decimal, so I'm going to say approximately, Control Enter. Are you getting negative 0.699-ish? Are we okay with this? Okay, so that's how you do these. I'm going to skip the 3.25. Let's do log of -4. So we're going to the calculator, and we're going to do log to the base 10 of -4. What's going on with that? So why is that not working? So if I have, Grace?
because you can't, you're saying that it's equaling -4 and nothing squared equals a negative number.
Well, we don't have to square. We're looking for the power, but we're saying 10 raised to what power gives us -4? And you're saying there's no number, there's no power I can put on 10 to end up with a negative number. All right, and that's significant because that means that's going to have ramifications for your domain for a logarithmic function, right? We're not allowed to plug in negative numbers into a log function. All right?
Does that apply to
All logarithmic functions, whatever the base.
So when the logarithmic function x cannot equal a negative number?
You cannot plug in a negative number into logarithmic function. So let's, I have that there. Let's back up and talk about this a little bit. So if I'm going to graph, let's say, I want one that's going to fit here. So let's graph f of x equaling 2 raised to the x. Nice exponential function like we graphed in section 3.1, right? When we graphed this, we made a little table of values, x versus 2 to the x. We picked like -2, -1, 0, 1, 2, something like that. So 2 to the -2 is that 1, 4? You with me? Yes? If 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4. I can maybe get one more here. 2 to the third is 8. So if I plot my original exponential function, here I get -2 is 1/4, -1 is 1/2, 0 is 1, 1 goes to 2, 2 goes to 4, 3 goes to 8. Wonderful, beautiful exponential function, exponential growth. Our base is greater than 1, right? But we already talked at the very beginning of this lesson, we said, hey, this passes the horizontal line test, right? Horizontal line is going to cross through the graph in at most one point, right? And that means it will have an inverse. Before we look at the inverse, can we talk about the domain and range for this function? The domain for this function is going to be what, Allison? Domain, how far left, how far right? All real numbers. So domain is -∞ to +∞. Everybody agree? How about the range? What's the range of this function going to be, Ryan?
It's going to go from not including 0 all the way to
All right, range is how far down, how far up. So not including 0. So you want like a parentheses?
Yeah.
0, comma, positive infinity. Do people agree with that? So our inverse, we studied inverse functions back in chapter 1. So you know that the inverse function is going to be mapping over the line y equals x. Remember that? Inverse functions are mirror images over the line y equals x. And how do we get them? We could just switch all the ordered pairs. Remember how we did this back in chapter 1? So that means with my inverse function, I can build up my ordered pairs just by switching all those, right? So 1/4 is going to go to -2. 1/2 is going to go to -1. 1 goes to 0. 2 goes to 1. 4 goes to 2. 8 goes to 3. Does that look okay? So if I plot these, 1/4 goes to -2. That's about here. 1/2 goes to -1. 1 goes to 0. 2 goes to 1. 4 goes to 2, 8 goes to 3. So this graph is going to be kind of hugging the y-axis, and then it's going to kind of go like this. It doesn't have a horizontal asymptote. It's going to keep rising, right? It's not leveling off, but it's just kind of rising slower and slower as it goes on. Okay, so this is our inverse function. Guess what kind of function that is? Logarithmic function. And the equation that we can write for this inverse function would be, I wrote this one as f of x equaling 2 to the x. I'll write this one as f inverse of x, right, because it's our inverse function. And that is going to be log, what's our base? What was our base here for our exponent? Exponential. What was our base for our exponential function? 2. So that's going to be our base here, log to the base 2 of x. So these should be ordered pairs that would fit with this. Let's just test a couple of them. Like if I try this one. If I plug 2 in here, what's log to the base 2 of 2? That's saying 2 raised to what power gets me to 2? 1. How about this one? If I plug in 4. Log to the base 2 of 4 says 2 raised to what power gets me to 4? 2. How about this one? If I plug in 8, 2, log to the base 2 of 8 says 2 raised to what power gets me to 8? 3, and so on, right? So that's this function. Can we talk about the domain and range for this function? Why would they be switched?
Because they're inverse.
They are inverses, so these should just be switched. So that means the range domain. The range here is going to be the domain here, so 0 to positive infinity, and the range is going to be the domain from here. Does that look like that's accurate with our graph? The domain goes 0 to positive infinity, not including 0. The range, negative infinity to positive infinity. Grace?
Will 1, 0 always be a coordinate on a log function?
Yes, log to the base anything of 1 is going to be equal to 0. As a matter of fact, that's a great segue into our properties of logarithms. So here are our properties. Are these on your gift? Probably not. No. Okay, so log to the base a of 1 is going to equal 0 all the time. This is just what Grace was asking about. And that's because a raised to the 0 is going to always equal 1. Our next, let me just give an example here. So if I log to the base 7 of 1, that's going to equal what? 0. All right, how about this one? This is saying log to the base a of a is always going to equal 1. And that's because a raised to the first is going to get me to a. So for example, what is log to the base 6 of 6? 1, because this is saying 6 raised to what power gives me 6? Well, 6 to the first power gives me 6. How about this property here? This one says log to the base a of a raised to the x is equal to x. Log to the base a of a raised to the x is equal to x. So, for example, if I have log to the base 3 of 3 raised to the 4th, that should equal 4, right? And that's really, I'm saying log to the base 3 of 81, right? 3 to the 4 is 81. So 3 raised to what power gives me 81? 4, right? So that property looks like that. And then this one says if you have a raised to the log to the base a of x, that's also going to equal x. All right? And what else do I have? This one says if you've got log to the base a of x equaling log to the base a of y, two logarithms that have the same base, then what you're taking the logs of have to be equal to each other. They would also refer to this as the one-to-one property. All right? An example for this last one? This would just be like if I have log to the base 2 of 3x minus 1 equals log to the base 2 of 5x, then 3x minus 1 has to equal 5x, and I can solve, right? Okay. All right, so I just did some practice problems like this. Well, let's see what we do. So what's log to the base 5 of 1, Dane? This is seeing if we can use these properties we just talked about. What's log to the base 5 of 1?
Would it be 0?
Would it be 0?
Yes.
Do people agree? That's because 5 raised to the what power gives me what? Well, it's 5 to the 0 power that's equal to 1. How about this one? What's log to the base squared of 11 of square root of 11? Julia. Is that going to equal 1? Do people agree? Sure. The square root of 11 raised to the first is equal to square root of 11. How about this one? 8 raised to the log to the base 8 of 30 is going to equal what? Grace J. 30? Yeah, that one's just equal to 30. And the way I would kind of prove this one, even though there's a log in it, this is really in exponential form. I've got something raised to the something equals something. Does that make sense? So this currently is in exponential form, and we should be able to go back and forth, right, from exponential form to log form. So if I wanted to rewrite this in log form, that's going to be log to the base what of what equals what? Can you fill in the blanks? This is not the star, hexagon, heart example, but it's similar, right? Rebecca?
Log to the base 8 of 30.
Log to the base 8 of 30 equals?
Log 8.
Yeah, equals log to the base 8 of 30, right? This 8 goes right here, this 30 goes right here, and this whole thing goes, does that make sense? That's how we're proving this. Okay, what else do we have? All right, let's skip that example. You get the idea with these? We're just going to set these 4 minus 3x equal to x plus 2 and solve. All right, let's do this one. This one looks more fun anyway. So we are trying this. So we've got log to the base 3 of x squared plus 4 equals log to the base 3 of 29. Jack, can you help me out with this?
You'd set x squared plus 4 equal to 29.
X squared plus 4 equals 29. Okay, and then what?
You're going to subtract 4 from the side.
Okay.
You get x squared equals 25, so then you're going to take the square root of both sides.
Okay.
You get x equals, would you do plus or minus? So x equals plus or minus 5.
X equals plus or minus 5. Do people agree with that?
Yes.
All right. One thing you do want to watch out for, though, is that when you do get a solution, it's got to work in the problem, meaning it's got to still be in your domain. So if you end up with something that's going to make you take the log of a negative number, got to kick it out. Say it's not going to be a solution. That would be an extraneous solution. Does that make sense?
Because x is being squared here, it can't be positive or negative.
Yes, you can plug anything you want in for x here because it's being squared. Exactly. Okay, so let's see what else we have. This one was graph, whoopsie, kind of want to.
I-
This is on your gift?
Yes.
Then why did I do the whole 2 to the x thing? If we're doing 3 to the x thing. I'll leave this one for you to do, because we did the whole 2 to the x thing. You with me? You know what I'm talking. Julia's shaking her head. What's wrong? Rachel?
So, would you have the solution x equals plus or minus 5, or you can only use the partial?
Actually, for this one, you could use either one. You do have to watch out for extraneous solutions, but here we could use either one, because if I plug in a -5 here, -5 squared is still going to give you a positive 25. Plus 4 is 29, so it matches. It's okay. But you're right, you got to watch out that nothing that you're taking the log of is going to be a negative number. All right, so this one I'm going to let you do on your own. Okay, the quick recap here is I would probably do -2, -1, 0, 1, and 2. You're going to plug those into your 3 to the x function. So what's that going to be? 1 over what? 1/9, 1/3. What's this one? 1, and then 3, and then 9. And then here you're just going to switch those ordered pairs, and then you're going to graph them on your. Did I provide you with a graph? Okay. And so then you'll graph them, and they're going to be mirror images, right, over the line y equals x. Oh, well, this is kind of a good follow-up question, though, for the 2 to the x example or the 3 to the x. Which of these is going to have a horizontal asymptote?
The first one.
The first one?
Yeah.
So exponential functions are going to have a horizontal asymptote. And the logarithmic functions are going to have vertical asymptotes. Garrett, you with us?
Sorry.
Okay. I know you're working on your graphs for a moment, but we're going to resume in just a second. All right, can you pause for a moment, and you're working on the graphs for that, and can we look at page 232? They've got kind of a nice summary of the characteristics of a logarithmic function on page 232. All right, on page 232, it says that logarithmic functions have one x-intercept and one vertical asymptote. All right, and the graph slowly rises for x greater than 1. They say that your domain is 0 to positive infinity. We talked about that. Range is negative infinity to positive infinity. We're on page 232. The x-intercept is 1, 0, unless there's been some shifting. Obviously, transformations are a different story, but we're talking about just the parent functions. It's increasing over its entire domain. It's a one-to-one function, so it has an inverse function. And the inverse of a logarithmic function would be a what?
Exponential.
Exponential function. And the y-axis is the vertical asymptote. It's a continuous function, no breaks, no vertical, well, there's vertical asymptote, but we're talking about the whole graph of it, right? From 0 to positive infinity, it's continuous, all right? And it's a reflection of the exponential function over the line y equals x. All right, so I wanted to just kind of highlight some of those things for this. Okay, at this point, let's talk about transformations. So if I have log to the base 3 of x as my parent function, and that's the one that you're graphing or have graphed or will graph on your GIF. What change has been made to get this function, g of x, log to the base 3 of x minus 1? Garrett?
Well, we, so we just shifted it down one, right?
Shift down 1. So this is shift down 1. All right. And then what about log to the base 3 of x plus 2? What kind of transformation is that, Jimmy?
Shift left 2.
Do people agree with that? Shift left 2. Okay. All right. That brings up the natural log function as opposed to the common log function, right? Common log, base 10, natural log, base e. All right? Just like we talked about the natural exponential function is e to the x, log to the base e of x is our natural log function. But we will hardly ever write it like this. We'll hardly ever write it like this. Instead, we will write it like this. It's got a special abbreviation, an L and an N and the X. And we read that ln of x. We're really just saying the letters, right? ln of x. All right? And I mean, I got to write it with like a little script here so it doesn't look like in, right? It's ln of x. Everybody with me? Okay? And that means log to the base e of x. So, just like we talked about earlier, y equals ln of x and x equaling e to the y are equivalent functions. All right.
Do we not write it with a capital L?
I think it's usually written like with a lowercase l, like that. I would just do a script, script ln of x like that. Okay, so let's make sure we can find the ln button on our calculator, and we're going to try actually this function, ln of x plus 1. So let's try f of x equaling ln of x plus 1, and we're going to plug in 73.25 for x. So on your calculator, if you do control and the e to the x button, you get the ln of x. So if we want ln of, I lost it already, 73.25, and then what was it? Plus 1. So I need to get out of that parentheses and then plus 1 on the outside. I'm getting 5.29-ish. Do you agree with that? Okay.
I got 4.307.
Your plus one wasn't
Yeah,
outside the
it's
parentheses.
gotta be outside.
Okay. And then how about, let's try plugging in 0.4 into this function. So what's ln of 0.4 and then plus 1?
0.084.
Does that look okay? 0.0837 or 0.084, something like that? Okay, how about if we plug in -2?
Not real.
Why not?
Negative.
We're not allowed to plug in negative numbers into our ln functions or any kind of log functions. The domain is 0 to positive infinity. No fair plugging in negatives. All right? And, well, we could plug this last one in, but you get the idea. All right, so I don't want you to write these down. Well, you can if you want. But these are the same properties except described in terms of natural log instead of just log to the base a, right, or whatever. These are specific to natural log functions. So ln of 1 is always going to equal 0. Remember, think of this as log to the base e of 1, right? So log to the base e of 1, this is saying e raised to what power gives me 1? And that would be 0, right?
Is that 1 or
Where?
another one?
This is log to the base e of 1. Oh, yeah. And then ln of e is always going to equal 1. And again, think of this as log to the base e of e. That's going to equal 1 because we're saying e raised to what power gives me e? 1. Right? So ln of e is always going to equal 1. ln of 1 is always going to equal 0. All right? And if we have ln of e to the x, that's going to always equal x. All right? And again, think of this as log to the base e of e raised to the x. So this is saying e raised to what power gives me e raised to the x power. I'll say that again. E raised to what power gives me e raised to the x. I say e raised to the x gives me e to the x. Does that make sense? So that's what this is all about. All right? And we could think of this way. E raised to the ln of x is equal to x. And again, the way I would think of, if I wanted to prove that this is true, I would take this from an exponential equation, I should say exponential form, and write it in log form, right? And so that would be log to the base e of x equals ln of x. You with me? And log to the base e of x is ln of x, so it works out. What else? If ln of x equals ln of y, then x has to equal y. That's that same one-to-one property kind of thing. And what else? And then I just had some examples. Are these on your gift?
Yeah.
Okay, so what's ln of e to the 1/3 going to equal, Rachel? Remember, you can think of this as log to the base e of e raised to the 1/3. Yeah, because this is saying e raised to what power gives me e raised to the 1/3 power. It will be 1/3. How about letter B? What's ln of e divided by 6? Dane? All right, let's talk about ln of e. ln of e is the same as log to the base e of e. So e raised to what power gives me e? I hear 0.
1.
I hear 1.
1.
It's 1, right? E raised to the first, right, is going to give me e, not e to the 0. E to the 0 is going to be 1. So what's ln of e equal to? 1. So this is really just 1/6. Sorry. Are we okay with this? Okay, how about e? We're on letter C. How about e raised to the ln of 8? Hannah? All right, well, let's put something. I'll put a box here. We don't know what it's going to be, but I know that this is currently written in exponential form, so let's rewrite it in log form. So that means log to the base what of what equals what? Hannah, can you help me out? Can you fill in the boxes?
Log to the e.
Log to the base e
Yeah.
of
Of
a box.
x
Yeah, box, whatever that is
equal to ln of 8.
is equal to ln of 8. And since we know that log to the base e is the same thing as ln of box, I get ln of box equaling ln of 8, so what has to go in the box? 8. So e to the ln of 8 is actually equal to 8. All right, what about 15 times ln of 1, Avery? What's ln of 1 equal to? Then you can think of this as log to the base e of 1.
Oh, 0.
So Avery, e raised to what power gives me 1? E raised to what power gives me 1?
0.
0. So that means that log to the base e of 1 is equal to 0, which means ln of 1 is equal to 0. So I get 15 times 0. That gives me 0 for this one. Are we okay with this? All right. I got like maybe 4 minutes before we have to get into our places for the ACT quiz. How much more do I have? This one? Oh, yeah. So we're almost done. Okay, so for this, it says find the domain of each function, f of x equaling ln of x minus 2.
X cannot, no. The domain would be 2
positive.
2 to positive infinity. Remember, we're not allowed to have any negative
No.
numbers.
It would be 1, or not including 1 positive.
So we can go down to 1.
No.
Can I have 1.5?
It's 0.
0 to positive infinity?
No. The first thing I said.
The first thing, all right, the first thing you say. Because x minus 2, are we even allowed to take the log of 0? No, it's got to be positive numbers only, right? So that means that this has got to be positive, so I can say x minus 2 has to be strictly greater than 0, right? So I just add 2 to both sides, and I get that x has to be greater than 2, as Rachel told us. And so in interval notation, we would use parentheses 2 comma positive infinity. How about g of x equaling ln of 2 minus x? Take a minute to work that out. What's our domain going to be for that? Rebecca, what do you think?
Negative infinity 2.
Negative infinity to 2, including the 2 or not?
Not including.
Not include. Do people agree with that? Because 2 minus x has to be greater than 0, right? And if I, like, let's say I just add x to both sides, I get 2 has to be greater than x, which means x has to be less than 2, which matches this. Let's take a quick look at that graph. ln of 2 minus x on the calculator. Go on the graphs page. ln, that's control e to the x. ln of, well, let me just get the parent function on there. There's my parent function, right? ln of x. And if I want ln of 2 minus x, tab ln of 2 minus x. So it's been reflected over the y-axis and shifted to the right too, in that order, right? And so that's why our domain is negative infinity up to 2, but we would have the vertical asymptote, right at 2. Okay? Are we okay with this? Okay. Skipping to, yeah, that was a good one. But well, I'm going to skip to this example just really quickly, just to give you a quick example. Students in a math class were given an exam and then retested monthly with an equivalent exam. The average scores for the class are given by the human memory model, which is a logarithmic function. 78 minus 17 times log of t plus 1, where t is between 0 and 12, where t is the time in months. So the students are tested every month, and what do you think? Are their scores going to get better?
Yeah.
No, they were studying, and then they test them every month. They're going to start losing what they learned, right? So the scores are actually going to start dropping. So what was the original score? You would plug in 0 for t, right? And see what you get. And then it says what was the average score after 3 months? So you could plug in 3 for t. You with me? And then, is there a follow-up? Yeah. What was the average score after 11 months? So you would just plug in 11 here and see what you get. Are we all right with this? All right, so I'm going to let, pardon me?
Can we just do that on the calculator?
Yes, you would just do this on the calculator. Okay. I mean, you could do it by hand. I don't know. No, you would do it calculator. Okay. All right, that is the end of our lesson here. Thanks for watching.